Dear students, welcome to this session. In this session, we are going to talk about a starter and what is the necessity of a starter in an induction motor. A starter is a device which will be required during the starting of an induction motor. And why it is required, what is the necessity? The induction motor is similar to a transformer with secondary winding, that is rotor winding, short circuited. So we have already seen the construction of the induction motor. We have a stator winding on the stator part, and then on the rotor part we have the rotor winding, and when a three-phase supply is given to the stator winding, it creates a magnetic field, and that magnetic field gets linked with a rotor winding. This is very similar to a transformer, where stator is similar to the primary winding. A supply is given, it creates a magnetic field, and that gets associated with a secondary winding, that is a rotor winding. Only difference here is in case of a induction motor, the secondary winding or the rotor winding is short circuited. Okay, the slip is initially high and results a higher induced EMF and current in the rotor winding, which in turn reflects on the stator. What happens is, in the last session we looked into slip. What is a slip? Slip is a difference in the speed between the synchronous speed of the stator field and the rotor speed, that is ns minus n, that is the slip. And during starting means what? The rotor is standstill, means it is not yet rotating, so n is equal to 0. During that time slip is very high, and slip is the value is 1. When slip is high, the amount of flux cut by the rotor conductors is very high, so the amount of EMF that is induced in the rotor conductors is high. And since the rotor winding is a closed loop or a short circuited, there will be a rotor winding which will be a very high rotor current, and this rotor current will get reflected on the stator, and it might cause a very high current to be withdrawn, and this is not safe for the equipment or the all the equipments that are connected in that particular system. So the initial current drawn by the induction motor is very high. To limit that current to a safe level, we require a starter. So what the starter will do, because the way induction motor works, its secondary is shorted, so it will result in a very high induced EMF, that in turn results a very high rotor current, that in turn gets reflected onto the stator, and that high amount of current is not desirable. So we want to have that current at a very safe level. And when the motor starts running, okay, the slip will start reducing. The EMF induced will also reduce in the rotor conductors, and the current will reduce. So this particular problem happens only during the starting of a machine. Okay, whenever you are trying to start the induction motor, that is when it causes a very high current, and once the induction motor starts running, it picks up the speed, then the current would be very normal amount of current, safe level of currents will be flowing. In order to reduce or limit the starting current, we will require a starter. So there are many different types of a starter. What we are going to see today is a star delta starter. What is a star delta starter? The star delta starter, here the technique is used whenever we are starting the machine. We will put the winding, we will put that stator winding in a star connection, and when the motor starts running to its full speed, when slip is low, then we will put to the delta winding. The reason for that is, when we have the star connection, we know that for each winding, how much would be the voltage? Whatever the voltage that is applied, that would be the phase voltage for the each winding would be V divided by root 3, means the voltage applied to each of the winding will get reduced by V divided by root 3. This is when during the starting, once the machine picks up the speed, once it starts running, then it will be given with the full voltage. So you can see here there is a full voltage. In case of a delta, the line voltage is equal to phase voltage. So if this is a 440 volt, the voltage applied across each winding is 440 volt. But in case of a delta, if applied voltage is 440 volt, 440 divided by root 3. So the voltage will reduce. How much it will reduce? It will reduce by 1 by root 3 times it will reduce. So we will apply a reduced voltage during the starting of a induction motor. So during starting we will put it in a star connection. So voltage is less. Naturally, when applied voltage is less, the magnetic field, the current will be less, the magnetic field created would be relatively less, and then the flux linking with the rotor winding will also cut that minimum flux. So relatively the amount of the current that is generated on the rotor winding is less. So once it starts picking up the speed, once it starts running with a full speed, then the induction motor is applied with the full voltage. Now this is the circuit diagram. This is the supply, 3-phase supply, and we have a main switch. Okay, you can see the main switch. This is the main switch. So basically this switch will have two position, on and off. On will make a connection, 3-phase connection to the winding. Off will disconnect all the 3 phases. So you can see all the phases are connected together or disconnected together, and this is connected to these 3 points. And here this is the stator winding, and you can see one end of these is connected to this side, and this is the switch. Okay, this is called as a star delta switch. So star delta switch means either it can put it in a star or delta. This is a star delta switch, and we have total 6 terminals. These are 3 terminals. Onto these 3 terminals, one end of the winding is connected, and the at the end we have 3 more terminals, and those are short circuited, and we have 3 more terminals in the middle, and the other end of the each winding is connected to the those terminals. So you can see this particular winding, it couldn't be RYB, any of these phases. You can see this winding is connected one end to this point and another end to this point. Similarly, the second winding, one end is connected to this terminal and another end is connected to this terminal. Similarly, the last one, this winding is connected to this terminal. Okay, and we have the winding and it is connected to the middle terminal. So this is the connection. Now you can see this is a star delta switch. Either it can be put on this side or on this side. When we put it on this side, it would be in the star connection. When we put this switch onto this side, it will become the delta connection. This winding will be automatically gets, when it is connected on this side, it will become a star connection. When this switch is thrown on this side, automatically it will become a delta connection. So during the starting of the machine, this switch is put on this side. Okay, and how will it make a star connection? You can see here 3 ends are connected to the supply, and the other 3 ends, okay, when they make a contact with this one, so this point would be connected to this point would be connected to this terminal would be connected to this. If you see, all of them are short circuited. So one end is short circuited, or one end of the winding is joined and other 3 are open. So we know that what connection is that? It is a star connection. See, one end is all the windings are connected or joined, the other ends are free. This is called as a star connection. During a starting, we put it in the a star connection. If you put it in the star connection, whatever the applied voltage V, how much voltage we see across each stator winding, V divided by root 3. So it will get reduced by 1 by root 3. Now once the machine starts running, this particular switch is thrown on this side, which is a run. So this is during starting. Once it picks up the speed, the switch is put on to this side. When the switch is put on to this side, this particular winding, three phases of the winding will get connected in a delta. So you can trace that. See, this end, this is the one end of the winding, the other end will get connected with this point, and that point is other end of the one more winding. Similarly, this winding will get connected to the second winding, and second end of the second winding will get connected to the first winding. So you can see the first winding. So this is how it makes this connection. So this 1, 2, 3, that connection. So that is how it forms a delta connection. So during starting of the machine, it is thrown onto the start, that it will make a star connection, and when it is running, it is put onto the delta. Why it is put onto delta? When motor starts running, it has to take the full load, so we need to apply the full voltage. Now when it is in the delta, the full voltage is applied across each winding. Next we will see the problems, very simple problems based on the induction motor. Very few formulas that you have to remember. One is for the synchronous speed, ns is equal to 120 f divided by p. Then slip, s is equal to ns minus percentage slip, ns minus n divided by ns into 100. And one more is the rotor frequency, rotor current frequency, that is f dash is equal to sf. Those are the three formula. Based on those three formulas, very simple problems will be there. So problem number 1, a 6-pole P is equal to 6 3-phase induction motor is connected to 50 Hertz, F is equal to 50. If it is running at 970 RPM, find the slip. Very straightforward. P is given, F is given, and what is 970? It is N, capital N. First we will find out the synchronous speed. What is synchronous speed? Ns is equal to 120 F divided by P, 120 into 50 divided by 6. So it will come as a 1000 RPM, 1000 RPM. So synchronous speed is 1000 RPM, and rotor speed is rotor speed or motor speed, anything is fine, is 970. Therefore, how much is the slip? Percentage slip is equal to ns minus n divided by ns into 100. 1000 minus 970 divided by 1000 into 100, that will come as a 3%, and if you represent it in the fraction, it will be 0.03. Next one is a 3-phase induction motor is wound for 4 poles. Okay, number of poles P is equal to 4 and is supplied from a 50 Hertz system. F is equal to 50 Hertz. Calculate synchronous speed. Number 1, speed of the motor when slip is 4%. The rotor current frequency when the motor runs at 600 RPM. So 3 sub questions are there. First is synchronous speed. Ns is equal to 120 F by P. Substitute all the values, we get 1500 RPM. Once we know what is the synchronous speed, we have to find a speed. They are asking a speed and they have given the slip. In this particular formula, this is given. We calculated ns, only unknown is n. So we can say 4% is given. We can say here 4 is equal to 1500 minus n divided by 1500 into 100. This into 100 is very important. When this is represented, this particular slip is represented as a percentage. If it is represented as a fraction, then you will not multiply with 100. You have to be careful with that. We get n is equal to 1440 RPM. The last thing we have to find is a rotor current frequency when motor runs at 600 rpm. So we have to find the rotor current frequency. Formula is f dash is equal to s into f. So f is given as 50 hertz. Now we have to calculate what is the slip at 600 rpm. What would be the slip at 600 rpm? Same formula, s is equal to ns minus n divided by ns. You have to remember here s is the fractional slip. Okay, it is not percentage, it is a fractional slip. Therefore s is equal to ns 1500 minus 600 divided by 1500. It comes as 0.6. Now the rotor current frequency f dash is equal to sf, that is 0.6 into 50 is equal to 30 hertz. So that is the rotor current frequency. Next one, a 6-pole alternator running at 1000 rpm supplies an 8-pole induction motor. Find the actual speed of the motor if slip is 2.5%. So this is a little bit tricky here. What I mean by tricky here is, instead of directly telling what is the supply, how much supply is they are giving, they have given a alternator. We know what is alternator. Alternator is a synchronous generator. It generates a 3-phase AC. They have given alternator specification, and this alternator supplies our induction motor. So all these parameters on this side is alternator values. So alternator has 6 pole and alternator is running at 1000 rpm. It supplies an induction motor, and induction motor has 8 pole. We have to find what is the actual speed of the motor if the slip is 2.5%. So what is the formula for the slip? Formula for the slip is ns minus n divided by ns into 100. For slip is given, we have to find n. To find n, we have to find ns. Okay, for finding the ns, what we need, ns is equal to 120 f divided by p. What is f? It is the supply frequency. What is the p? P is the number of poles on the motor. So induction motor. Okay, now f is not given, but they said they have given the specification of the alternator. So alternator specification is given. Using this alternator specification, I can find out what is the frequency. What is the frequency of the alternator supply? F is equal to n into p divided by 120. If you remember, we did this derivation. F is equal to n into p into 120, where n is the speed of the alternator 1000, p is the number of poles of our alternator, divided by 120, we get it as 50 hertz. So 50 hertz is the supply. Using that value, you can calculate 120 into 50 divided by p. This is the number of poles on the induction motor, 8. We get it as 750 rpm is the synchronous speed. Therefore slip s is equal to ns minus n divided by ns into 100. What we have to find? We have to find the actual speed of the motor when slip is 2.5%. So formula is 2.5 is equal to 750 minus n divided by 750 into 100. So we get it as n is equal to rotor speed is equal to 731.25 rpm. Next problem, a 50 hertz 4-pole 3-phase induction motor has a rotor current of frequency 2 hertz. This is f dash. Determine the slip and speed of the motor. F is given, f is equal to 50 hertz, p is equal to 4-pole, and f dash is 2 hertz. We know the formula, f dash is equal to sf. F dash is given, f is given. So slip is how much? S is equal to f dash by f, that is 2 by 50. We get it as 0.04. It's a fractional slip, or it is 4%. Then what we have to calculate? Speed of the motor. In order to calculate the speed of the motor, first we have to find the synchronous speed. What is the synchronous speed? 120 f divided by p. That is 120 into 50. 50 is given, and 4, that is number of poles, is given. we get synchronous speed as 1500 rpm. S is equal to ns minus n divided by ns. S we have calculated, and synchronous speed we have calculated, only unknown is n. So 0.04 is equal to 1500 minus n divided by 1500. We get the motor speed as 1440 rpm. Next one, 500 horsepower. Okay, this is additional information, we won't need it. 3-phase 440 volt 50 hertz induction motor has a speed of 950 rpm on full load. The machine has 6 poles. Calculate the full load slip. How many cycles will the rotor voltage make per minute? So here a few things, additional things are there which you may not need. So don't worry if additional information is given. 440 is given, which is not required. 500 HP is not required. Frequency is required. F is equal to 50 Hz. N 950 RPM. And it is running on full load. Don't worry about what load it is. Just it is running. They have mentioned it is running on the full load. We have to calculate full load slip. Just you read it as calculate the slip. That is sufficient. And the machine has a P is equal to 6. Then also we have to find how many cycles will the rotor voltage make per minute. So they have asked the rotor current frequency in different terminology. So what they are asking is a rotor current frequency. How many cycles will rotor voltage? So we did the derivation for the rotor current. Same applies for the rotor voltage. Make per minute. When we say frequency has always rotations per cycles per second. Okay, so we want to say cycles per minute. So we instead of giving it in terms of a second, we have to tell it how many cycles it will make per minute. That is the difference. First we will find the synchronous speed. Ns is equal to 120 F divided by P. 120 into 50 divided by 6. 50 is given and 6 is given. Okay, 1000 rpm. And what is the full load speed? 950 rpm. How much is the slip? S is equal to ns minus n divided by ns, calculated in fractional slip. That's why we don't have the multiplied by 100. 1000 minus 950 divided by 1000, it will come as 0.05, or it is 5%. Now what is the frequency of the rotor EMF? Frequency of rotor current and frequency of rotor EMF both are same. Okay, don't get confused, both are same. F dash is equal to SF, that is the formula. So F dash, how much I get? 0.05 into 50, 2.5 hertz. 2.5 hertz is what? Hertz is nothing but cycles per second. And what we have to give? Cycles per minute we have to tell. So what we will do? We divide multiply this with 60. Therefore complete cycles made by rotor voltage per minute is 2.5 into 60. We get it as 150 cycles per minute. You should write the unit here, cycles per minute. Next problem. A slip ring induction motor runs at 290 rpm. N is equal to 290. At full load, when connected to 50 Hz supply, F is equal to 50 Hz. Determine the number of poles and slip. So here we have to determine number of poles and as well as slip. There is a lack of information. The information is not complete here. So here most of the time they may not ask such questions where there is a data deficiency. Here what you can do is either we can say the synchronous speed. See, 290 is the rotor speed, and we can make a very nearest speed which gives a rounds figure. Means what? 290. What is the closest number? 300, and it is round. 290 and 300 is the probable or assumed value of the synchronous speed. You can assume and you can do the calculation, right? See here, the full load speed of an induction motor is very close to synchronous speed. The full load slip is less than 3%. Also you have to make sure when you are taking the next number, you might ask me why we didn't take 350 rpm, why we took 300 rpm. So you have to make sure that the slip is very close to or less than 5%. Okay, it should not be more than 5%, and you can select accordingly. So it is reasonable to assume that ns is equal to 300 rpm. So with synchronous speed assumed as 3300 rpm, we can do the calculation. Now ns is equal to 120f divided by p. 300 is equal to 120 into 50 divided by p. Therefore p is equal to 120. And if you calculate the slip, ns minus n divided by ns, 300 minus 290, 3 divided by 300, 0.0333 or 3.33%. So why we assumed 300 as the synchronous speed? We get around 3.33% of slip, which is below 5%, that is acceptable. If you take 350, just take it as 350 and do the calculation. So you will get a very large value for the slip. So it would be 350 minus 290 divided by 350. So that is not a acceptable value of the slip when machine is running on full load. Next problem, a 10-pole 3-phase alternator is coupled to an engine running at 600 rpm. It supplies a 3-phase induction motor which has a full load speed of 1440 rpm. Calculate the number of poles and slip of the motor. Again you can see here alternator is coupled to an engine running at 600 rpm. So how alternator is running? See, first scenario is this alternator is supplying our induction motor, and how this alternator is being driven? So it is being driven by some mechanical device. So what is alternator? It converts mechanical energy into electrical energy. How that mechanical energy is produced? Using an engine. That engine is coupled to alternator, and that engine is running at 600 rpm. You can say the speed of the alternator is 600 rpm. Number of poles on the alternator is 10. And any other information? Okay, those are the two information. Basically, when you see a alternator in case of a induction motor problem, most probably that is given so that you can calculate the frequency. So now it supplies 3-phase induction motor which has full load speed. N is 1440 rpm. Calculate number of poles and slip of the motor. So we have to calculate P on the induction motor and percentage slip on the induction motor. And what is the frequency of the alternator? It is given by F is equal to N into P divided by 120. N is the speed of the alternator. P is number of poles of the alternator. So 600, that is the speed of alternator. 10 is number of poles. 600 into 10 divided by 120, we get it as 50 hertz. Now synchronous speed of the induction motor, ns is equal to 120f divided by p. Now you can see p is not given, right? We need to find the p value, and without p value we cannot calculate the synchronous speed, and without calculating the synchronous speed we cannot calculate the slip. Now again here there are two unknowns. The same assumption goes here. You can assume a very close value, so 1440, right? 1440 which is the closest number, 1500. Either you can do that, right? Assume that ns is equal to 1500 synchronous speed, and then calculate the number of poles, or go the other way. You take, this is how much, 120 into 50 divided by p. You take the number of poles as 2. Okay, you will find, okay, here it is, p is taken as 2, then we get the synchronous speed as 3000. But what is the motor speed? Full load motor speed 1440. There is a huge difference between those two numbers. We want a slip around 5%. then we will make P is equal to 4. Always P is in terms of a pair of poles, right? 2, 4, so on. Ns is equal to 1500 rpm we get. So this 1500 is very close to this. Since the full load speed of the motor is close to synchronous speed, probably Ns is equal to 1500. Therefore P is equal to 4. So number of poles is 4. Now slip, how do we calculate? S is equal to Ns minus N divided by Ns. 1500 minus 1440 divided by 1500, we get it as 0.04, or this is the 4% slip. So there would be very simple problems based on the induction motor. 3 simple formulas, you work out all these problems again. That will get you more confidence. Also in the book I did not give all the tutorial problems, but in the VK Mehta book there are more problems in the tutorial problem section. You can look up that and you can solve. Here there are 2, just I have included for your reference so that you can try to solve this, whose answer is given here.